Okay, so today's notes are on solving systems with elimination, and our content objective is going to be to solve linear systems algebraically with elimination. Our language objective is to use the correct terminology when explaining the process of solving linear equations with elimination, or linear systems with elimination. So just as a reminder, there are 4 ways to solve a linear system. We've done graphing in 3.1. We did substitution. And today we're doing elimination. And we'll try to squeeze in a day with calculators to go over matrices and graphing again. But today is our focus on elimination. Okay, so let's jump in with an example. I want us to figure out what is the solution of the system of equations for 4x plus 2y equals 9 and negative 4x plus 3y equals 16. So there's our system, 4x plus 2y equals 9, negative 4x plus 3y equals 16. So elimination, what we're going to do, for our step here, it's more of a reasoning thing for the first part. Since 4x and negative 4x are additive inverses, we're going to add the 2 equations and vertically, just so we can visually see it, to cancel out x. So again, the vertically is more just for visual sake. It's not an actual math reasoning thing, but we're going to add it vertically so we can see what we're doing. So if I rewrite my 2 equations, if I add these straight down, I do 4x plus negative 4x, they cancel out. So then I add 2y plus 3y and I get 5y, and 9 plus 16 and I get 25. So at this point, I now have only one variable, which means I can solve. So the goal of solving a system is to get an equation with only one variable. So you can solve for it and then plug in and solve the other one. So now with elimination, we've successfully eliminated the variable x, so we can solve out for y. So that is our step 2. Solve for y. So I divide both sides by 5 and I get y is equal to 5. And then just like we did with substitution previously, now I can substitute back in and solve for x. To solve. So I'm substituting into one of the original equations. So if I plug into one of the original equations, I'm going to use the positive 4x plus 2y equals 9. So again, I'm plugging in 5 for y there, and I get 4x plus 2 times 5 is equal to 9, which then I get 4x plus 10 equals 9. I subtract 10 from both sides, and 4x is equal to negative 1. I divide both sides by 4, and I get x is equal to negative 1/4. So now I've successfully solved for y and x. I can write my final coordinate. So then I have negative 1/4 for x and 5 for y, and I have successfully solved my system. I can always go back and plug them in to check that they are the correct solutions, but for the sake of time, I'm going to skip that now. So let's do a really quick check together. So I want you guys to, again, solve using elimination. And we have negative 2x plus 8y equals negative 8. And 5x minus 8y is equal to 20. So try that one on your own, pause it, give it a try. I'm going to go over it now. So again, I can see that the y's are additive inverses here. So I'm going to do negative 2x plus 8y equals negative 8 over 5x minus 8y equals 20. If I add these down, I get negative 2 plus 5, which is 3x. Positive 8 and negative 8 cancel each other out. Then negative 8 plus 20 is going to give me positive 12. So I end up with 3x equals 12. I'll write that closer together so you can see it. I divide by 3 and I get x is equal to 4. I'm going to plug that back into one of my original equations, so I'll just use the first one. So I have 2x plus 8y equals negative 8. And I'm going to plug that back in for x up here. Negative 2 times 4 plus 8y is equal to negative 8. So I get negative 8 plus 8y equals negative 8. I add 8 to both sides and I get 8y equals 0. So y is just 0. So my final coordinate point is 4, 0. And that is our solution. All right, so at this point you might be thinking, this is great if I just have two equations with additive inverses, then that will be super easy, but how will you use elimination if they're not additive inverses from the get-go? So if they're not additive inverses from the get-go, we can make what are called equivalent systems, or equivalent, So equivalent systems are two equations, or when you get equations, or what you get when you multiply each side of an equation by the same non-zero number. Ultimately, when you make equivalent equations so that you can use a process like elimination, but it's when you multiply a linear equation all by the same number, it's equivalent. They have the same solution. So you're not changing the value of anything because you're multiplying them all by the same number. So you can do that to use a process like elimination when you're not starting out with additive inverses. So let's do an example of this together. So what is the solution of two x plus 7y equals 4 and 3x plus 5y equals negative 5? All right, so what we're going to do here, step 1, we're going to determine a common multiple for the coefficients of one variable. So a common multiple is a number they both go into. 4. So we're going to look at the coefficients of x and y and see which of those have a common multiple that will be easy to multiply or be easy to get. So I could do 2 and 3 both go into 6, 5 and 7 both go into 35. 6 is a lot lower than 35, so I'm going to reason through this and choose the easier number. So I have 2x plus 7y equals 4 and 3x plus 5y equals negative 5. So I have my two equations. What I'm going to do is multiply to get each equation, multiply each equation to get coefficients that are additive inverses. So I know I can multiply 2 and 3 by numbers to get a common multiple of 6. So I'm going to multiply this equation to get 6. I need to multiply by 3. So I'm going to multiply everything in that equation by 3. And when I do that, I distribute in. 2 times 3 is 6x 7 times 3 is 21y, 4 times 3 is 12. So that becomes my new equation there. Here, if I want additive inverses, if I just multiply by 2, I'll get 6, but since I want them to cancel, I'm going to multiply by -2 so that they will, when I add them, they'll cancel out. So I'm going to distribute that all in. I get -6x minus 10y equals positive 10. So that's my new equation, or my two new equations, equivalent system, if you will, when I multiply to get additive inverses for one of my variables. So I'm going to now add straight down, and now we're just doing a process like we just did with our other elimination. So these cancel out, and I'm left with 21 plus -10, which is 11y equals 12 plus 10 is 22. So y is equal to 2. So now I'm just solving just like we did previously. So now I have 2. I'm going to substitute into my original equation, or one of my original equations. I'm going to use 2x plus 7y equals 4, and I'm going to plug in for y here. So I have 2x plus 7 times 2 equals 4. So 2x plus 14 equals 4. 2x equals -10. So x equals -5. And then now I have my coordinate point. So then my final coordinate is going to be -5, 2. And we're done. So the main thing here is the multiplying. You have to find a common multiple that you will get here that is an additive inverse that you can cancel out. So let's do a quick check together really fast to see if you guys are understanding. So I want us to again solve with elimination. We have 3x plus 7y equals 15, and 5x plus 2y equals -4. Pause this, try it on your own. I'm going to go over it now. So when I'm figuring out what I'm going to multiply by to get additive inverses, I could multiply by 5 and 3, or I can multiply by 2 and 7. It doesn't really matter. I'm going to choose to change my y values to be additive inverses. If you did it differently, just look at the solution at the end and see if you get the same thing. If so, you should be all set. So I'm going to start with 3x plus 7y equals 15, and 5x plus 2y equals -4. And I'm going to multiply my first equation by 2. So I'm going to change this. I'm going to multiply it by 2, and this one, to cancel out my y's, I would have to multiply by -7. So I'm multiplying my second equation by -7. So when I do that, I get 6x plus 14y equals 30. And for my second equation, when I multiply it, I get -35x minus 14y equals positive 28. Now I'm adding straight down as we do with normal substitution, and I get -29x. The 14y's cancel out, and that equals 58. So -29x equals 58. If I divide by 29, I get x is equal to -2. Now I'm going to substitute that back into one of my original equations. So I'm going to use 3x plus 7y equals 15. I'm going to plug that back in for x over there. And I get 3 times -2 plus 7y equals 15. So I get -6 plus 7y equals 15. 7y is equal to 21. So I added 6 to both sides. So y is equal to 3. Thus, my final coordinate is -2, 3. So if you chose to change your x values, as long as you got the final solution of -2, 3, I'm sure you did it correctly. Make sure you write down any questions, comments, or concerns you have on this process so we can go over them together in class. But that is all for now.